Example 2. The mass and spring of example 1 are now attached to a dashpot that provides 1 Newton of resistance for each meter per second of the velocity. The mass is set in motion with the same initial position y of 0 equals to 1 meters and initial velocity v0 equals to minus 5 meters per second. Find the position function of the body as well as the pseudo period of the oscillation and the new time lag of its motion and the times of its first 4 passages through the equilibrium position y equals to 0. Okay, so use our information from example 1. We know m equals 1/2 and the k equals to 50. And here, because C, so we know the damping force equals to negative CV, and here C is 1 Newton per 1 Newton per second for each meter per second of the velocity. Okay, so we have Newton per meters of the per seconds of the velocity. Okay, so let's put it in. We have my prime prime plus cy prime plus ky equals to 0. M is 1/2. C is 1. K is 50. Okay, so let's multiply both sides by 2 to get rid of the 1/2. So when we multiply by 2, this becomes 2y prime. This is 100y equal to 0. So what is the characteristic equation? So the characteristic equation is r squared plus 2r plus 100 equal to 0. Okay, so when we try to solve for r, let's solve for r. R equals to, by the way, we can see we're not able to factor it, so let's use quadratic formula. So 2a is 1, negative b, negative 2 plus or minus b squared, minus 4ac. So the answer is negative 2 plus or minus, this is like negative 99 times 4. Square root of 4 is 2, and then square root of 99i over 2. So the answer is negative 1 plus or minus square root of 99i. Okay, because we have 2 complex roots, so we have under damped case. Okay, so the solution is a times our alpha is minus 1t, so minus t, and then cosine square root of 99t. All right, plus b e to the minus t sine square root of 99t. So far, so good. Oh, by the way, what's square root of 99? Well, that's the same as, so 9 is 3 squared. So 3 square roots of 11. Okay, so let's use 3 square roots of 11 here and there. You can keep 99, square root of 99, of course. Okay, so next, well, let's figure out a and b. So our initial position is 1. So 1 is, we plug in t is 1, e to the 0 is, sorry, we plug in t is 0, e to the 0 is 1, cosine 0 is 1. So a is 1, right? And then y prime of t, well, we gotta use product rule here. So product rule, this is so important. Okay, so product rule, first guy, second guy. The derivative of the first guy is minus a e to the negative t times second guy plus a e to the negative t derivative of the second guy. That's derivative of cosine is minus sine. Chain rule. Okay, and then, yeah, we're gonna have 4 terms. Derivative of the first guy is minus b e to the negative t sine 3 square root 11t. Derivative of the second guy, derivative of sine is cosine times chain rule. Okay, now we can plug in 0. So v prime of 0 is the initial velocity, which is negative 5. So let's plug in 0 for t. E to 0 is 1, cosine 0 is 1, sine 0 is 0. So this is all gone. And sine 0 is 0, so this is all gone. Okay, and then the last term b, e to 0 is 1, cosine 0 is 1, and then we have 3 square roots of 11. But a is 1, so let's plug in a is 1. When we move to the a to the other side, we get minus, so we get 3 root 11b equals to negative 5 plus 1, which is negative 4. So b equals to negative 4 over 3 square roots of 11. So far, so good, everybody? Okay, now what is c? Okay, so c is then square root of a squared plus b squared. A squared is 1, b squared 4 times 4 is 16, and then that is 99. So 99 plus 16, that is 115. So far, so good, everybody? Okay, so that is C. And then let's continue. All right, so what is alpha? Well, alpha equals to, so we know tangent. So alpha, let's look at A and B. So our A is 1. B is negative. Oh, B is also negative. So negative, let's say this is 1, this is negative 4 over 3 square root of 11. Okay, so we're still in the 4th quadrant. So alpha is 2 pi plus arctangent of B over A. So B over A, but our A is 1, so it's just this number. So let's plug this in our calculator. So 2 pi plus arctangent. So make sure you're in the radian mode. 3 arctangent negative 4 over 3 square root of 11. So my answer is 4.93478. Okay? So let's continue. All right. So what is asking? What a position function, okay, as well as the pseudo period of the oscillation and new time lag. Okay, so the pseudo period equals 2 pi over our imaginary part. Our imaginary part is 3 square roots of 11. Okay, so that's approximately equals to 0.6315. Okay, so that's the period. And then what is the time lag? Oh, sorry. I realized that my alpha was wrong. So when I divided by 3 square root of 11, I forgot to put a parentheses around it. So it becomes divided by 3, but times square root 11. So let me insert a division there. Okay, so my answer should be, so when you type the number in your calculator, you have to be very, very careful, because sometimes you miss a parentheses, then it's wrong operation, we get a wrong number. So it's very important to practice using your calculator. Okay, and then the new time lag is the alpha over the omega 1, which is 3 square roots of 11. Okay, so my alpha divided by 3 and divided by square roots of 11. I got 0.593067, so 7. So far, so good, everybody. So our function is c is square root of 115 over 99 e to the negative t, and then cosine omega, which is 3 square roots of 11 t minus alpha is 5.9009. So far, so good, everybody. Okay, next, it also asks the times of its first passages through the equilibrium position. Okay, so through equilibrium position, which means you want to find the first 4 times such that y of that time is 0. Okay, so, well, you know, this is like the cosine. Okay, you want to find where is the cosine 0. Okay, so that means, okay, what's the things inside my cosine? So you need this guy. Okay, so when is this guy 0? That means the angle inside my cosine should be pi over 2 plus k pi, right? Because when pi over 2 is 0 and 3 pi over 2 is 0 and is negative pi over 2 is 0, so k is any integer. Okay, so let's solve for t. Well, then t is pi over 2 plus k pi plus 5.9009 over 3 square roots of 11. Okay, so we want to find the time that's greater or equal to 0. Okay, so what number of k can make this guy greater or equal to 0? So let's make a table. Okay, so the first time, second time, and the third time, and the fourth time. Okay, so what is the k values such that when we plug it in, then the t is positive? Okay, let me plug in. So the denominator is always positive. Okay, so we want to have like a k such that let's figure out what's pi over 2 is like 1.7. 1.7 plus 5.9 is 7.6. Okay, so k is, we want to pick the k to be negative number. So what negative number we can add to it? So pi, you know, pi is 3. Pi is like 3.14, right? So when k is negative 2, then we get positive number. Okay, so let's put it in. Okay, so when k equals to negative 2, let's put it in, and when k equals to negative 3, let's put it in, and when k equals to negative 1, let's put it in to make sure, okay, which one is the t value such that it's greater or equal to 0. Okay, so let's plug in k equals to negative 2. So we have pi over 2 minus 2 pi plus 5.9009 divided by 3 and divided by square root of 11. Okay, so I got this is 0.11944. Oh, 945 actually. Okay, because the next digit is 9. Okay, and then when we plug in 3, so we don't need to type the whole thing again. Just go up to our equation and then change the 2 to the 3. Oh, we get negative 0.19629. So because it's negative, then we know k equals to negative 2 is the first time it passed through the equilibrium position. So t is 0.11945. And the second time, so this corresponds to k is negative 2. Second time corresponds to k equals to negative 1. Okay, so let's plug in negative 1. Then we have 0.43519. Okay, the third type corresponds to k equals to 0, and this is k equals to 1. So when k equals to 0, then we have, let me see. Let's see. Then we have 0.750933, so 3. Okay, and the next one we have 1. So 1 means in some negative part we have at. Okay, so my answer is 1.06665, so that is 8. Okay, so those are the first 4 passages through the equilibrium position. So far, so good, everybody? Okay, let's continue to look at example 3. The following problems are about free damped motion. A mass M is attached to both a spring with given spring constant K and a dashboard with given damping constant C. The mass is set in motion with initial position x0 and initial velocity v0. Find the position function y of t and determine whether the motion is overdamped, critically damped, or underdamped. If it is underdamped, write the position function in the form of, okay, this guy. Alright, so let's calculate this. So I hope you can pause the video and try to work on this problem. And after you're done, we can check our answer. Okay, so are you done? Let's work on it. So our formula is my prime plus cy prime plus ky equal to 0. Now let's plug in the numbers. So m is 3, c is 30, k is 63. Okay, then what is the characteristic equation? That's 3r squared plus 30r plus 63 equal to 0. Okay. Oh, can you see all the factors? So all the terms have a factor of 3. So let's divide it by 3. And this is 21. Okay. And then can we factor it? Oh, yes. That is 7 and 3. Right? So r is negative 3 and r is negative 7. So for this mass spring motion, your r is always negative if it's real numbers, okay? Or if it's a complex numbers, the real part is negative. Okay, so what is our solution? Well, the solution is then y of t is a e to the negative 3t plus b e to the negative 7t, because we only have the exponential terms. So this is over damped case. Okay, and let's figure out the constants. Well, what's y0? Okay, y0 is 2, so 2 is y0. We plug in e, t is 0, so a times 1, b times 1. Okay, for y prime, let's differentiate. Derivative is negative 3a e to negative 3t minus 7b e to negative 7t. Okay, so when we plug in 0, what happened? Negative 3a, negative 7b equals to, what is that? Y prime is velocity, which is also 2. Okay, so let's see, what do we get? Okay, so here we have 2 equations, 2 unknown. You can just solve the equation, or you can put them in a matrix and solve it. Okay, let's put it in a matrix. Okay, 1, 1, 2, and negative 3, negative 7, and 2 as well. Okay, so how do we get rid of this guy? 3r1 add 2r2. 3 minus 3, 0. 3 minus 7, negative 4. 3 times 2, 6. 6 minus 2. 6 plus 2. 6 plus 2 is 8. Okay, so that is A, this is B, this is the right-hand side. So we have negative 4, B is 8. Well, then B is 8 over negative 4, which is negative 2. And then we plug in the first equation, A plus B is 2. Oh, then A is 2 minus B, so 2 plus 2, which is 4. Oh, so our solution, A is 4, so 4e to the negative 3t. B is negative 2, e to the negative 7t. So far, so good. So this is our final solution for this problem. Okay, and overdamp case. You can also try to plug this functions into like a GeoGebra software to see what the function looks like. I just type it in the calculator, and this is what we get. All right, let's continue. Okay, so next we have m equals to 4 and c equals to 20, k equals to 25, and y of 0 is 2, v of 0 is minus 1. Okay, so what is our formula? My prime prime plus cy prime plus ky equal to 0. M is 4, c is 20, the k is 25. So, you can see what's the characteristic equation? 4r squared plus 20r plus 25. Do you realize this is a complete square? 4r squared is like 2r squared. 25 is like 5 squared. So this is like 2r plus 5 complete square, right? The middle guy is 2ab, so 2 times 2 times 5 is 20. Okay, so now the roots, we have negative 5 over 2, and with multiplicity 2 is the repeated roots. So the solution looks like A, e to the negative 5 over 2t plus b, t e to the negative 5 over 2t. So far, so good. And then we can find the constants A and B using the initial condition. So y of 0 is 2. When we plug in 0, A e to 0 is 1. B times 0 is gone. So A equals to 2. Yay! Y prime of t is derivative of that is negative 5 over 2a e to the negative 5 over 2t. But the next term, we need product rule. So the derivative of the first guy is just b. And derivative of the second guy, you have an extra factor of -5 over 2 e to -5 over 2t. Okay, so let's plug in y prime of 0, -1. So -1 is y prime of 0. We plug in t is 0, e to the 0 is 1. And b here we have a t, so it's gone. Okay, so a is 2. We plug in 2, so -1 equals -5. 2 and 2 cancel, so plus b. B is then -1 plus 5, which is 4. Oh, okay. So our y of t is 2 e to the -5 over 2t plus 4t e to the -5 over 2t. And when we see repeated real roots, we know this is critically damped case. Okay, so what does this look like? Let's see. Okay. All right. So let me type it here. Y equals to 2 e to the -5 over 2. Here we're using x, okay? But because how we type it, they assume the horizontal axis is x-axis, so we change to x. But for your solution for the problem, we're using t, okay? We're doing application problem, so we have t. Oops. E to the -5 over 2x. Okay, so this is a picture. Okay, so this is a picture of it, and it's a critical damped case. Yeah, it really looks similar to the first one, right? Oops. Okay. All right. So you can see they're quite similar actually. Okay, but the red line is can I change the color? Setting. Can I change the color? Okay, now I changed the color. So now I can see the difference between red and green. I cannot quite see the difference between red and orange. How about you? So the red one is our part A. Okay, our part A is our overdamped case. And then our part B is critically damped case. So you can actually see it pass through the t-axis once. But that is when t equals -0.5. So that's why when we're looking at the t greater or equal to 0, then it does not pass through it. And sometimes it happens. Sometimes if your t, it really depends on your initial condition. So sometimes maybe the t-intercept is greater than 0, then you're able to see it pass through the t-axis and then approach to 0 again. Okay, so you can see the difference between critically damped and underdamped case. Critically damped and overdamped case. How about the underdamped case? Yeah, we can also plot that. We have that example. Okay, so this is the example. Let's plot it in. Okay, so we have a lot. Let's plug in this one. Okay, so keep that in mind. Let's plot it. So this is y equals to square root of where's square root? Here. Square root of this is 115 over 99. And then we have e to the -t outside of the square roots. E to the x. Okay, yes, that's how you can plot it. So then cosine of 3 times square root of 11. and then x minus what I forgot that number. 5.9009. Okay. 5.9009. Okay, so you can see the what happened? Okay, so why is that? So okay, so it's e to the negative x. What happened? Did I type something wrong? E to the negative x. Something wrong with Algebra. I don't know why they put a here. Okay, so how about if I put it in front? E to the negative x. Something wrong with it. Yeah. Let me figure out what's wrong. Okay, so actually I manually compute the square roots of 115/99. That's approximately 1.0777. So, and then I type this in the Algebra calculator, and you can see this is the underdamped case. Is it getting close to 0, but it still have the oscillation. Okay, so the red line is the overdamped case. The green line is the critically damped case. It can pass through the t-axis at most once. And then the blue lines is the underdamped case, okay, where we have all the oscillation. All right, bye.